Hello again. This is Math 2134 coming to you from the College of DuPage, and the title of this lecture is L'Hopital's Rule. As always, I recommend you be an active learner while watching this video. This is Appendix B in your textbook, and the title is Indeterminate Forms and L'Hopital's Rule. So what we're going to do is we're going to talk about what indeterminate forms are, and then we're going to find the limit of an indeterminate form of the form 0 over 0 or infinity over infinity using the L'Hopital's rule. We're also going to learn that by doing algebra, we can find the limit of an indeterminate form of the form 0 raised to the 0 power, 1 to the infinity, or infinity to the 0, using L'Hopital's rule as well. Finally, we're going to use algebra to find the limit of the indeterminate form infinity minus infinity, using L'Hopital's rule. By way of introduction, way back in Chapter 1, we showed that the limit as x tends to 1 of x squared minus 1 all over x minus 1 is equal to 2. You might remember what we did back then is we factored the top into x plus 1 and times x minus 1, and then we canceled out the common factor. Today we're going to talk about another way to get this, and what we're doing today will work even when you cannot factor the numerator and denominator. Okay, so this is the one we're considering, and we'll show how L'Hopital's rule can be applied to get the tool. Now, to get the 2. Note that as x approaches 1, both the numerator and denominator approach 0. So what we would have if we try to just plug it in is an indeterminate form 0 over 0, because 0 over 0 is meaningless. Another common indeterminate form is infinity over infinity, and L'Hopital's rule can be applied to either one of those, as the title illustrates. And this happens when x approaches some value a, both the numerator and denominator increase or decrease without bound, so it gets infinity over infinity. When we attempt to evaluate a limit by substitution and get an indeterminate form, the limit may exist, and we have to use some other method than directly just plugging it in, either finding a common factor and canceling it, or some other algebraic technique creating a common factor. So in Chapter 1 we did this both with algebraic and numerical methods. Here we're going to use differentiation to find the limit exists using a rule called L'Hopital's rule. And this is what L'Hopital's rule says. If f and g are differentiable over an open interval containing x equal a, although not necessarily at a itself, if the limit as x tends to a of f of x over g of x is 0 over 0, or the limit as x tends to a of f of x over g of x is equal to plus or minus infinity over plus or minus infinity, and if this limit as x tends to a of f prime of x over g prime of x exists, then the limit as x tends to a of f of x over g of x is equal to the limit as x tends to a of f prime of x over g prime of x. Now, I am going to tell you straight up that one of the biggest mistakes students make is that they think you're taking the derivative of the quotient. This is not the derivative of the quotient. It's the derivative of the numerator divided by the derivative of the denominator. The derivative of the quotient is g f prime minus f g prime all over g squared. So you see it's this instead of the derivative of the quotient. And there's a proof that's in one of the exercises that is in your appendix. So anyway, here's some guidelines. When using L'Hopital's rule, we first check, in fact this is how we decide to use L'Hopital's rule, we first check whether f of x over g of x gives an indeterminate form by substituting x equal to a. And again, you remember this just plug it in was the first thing we always tried. If we obtain an indeterminate form, we then differentiate the numerator and the denominator of the original expression separately. Again, it's not the derivative of the quotient. Then we evaluate the limit of the ratio of the derivatives, and that, by L'Hopital's rule, is the same as the original limit. Examples are worth 1,000 words. And by the way, we could have done this in Chapter 1 as well. In fact, we did, and we factored the numerator and denominator and canceled out a common factor. But here, what we're going to do is we're going to use L'Hopital's rule to illustrate it. So if we evaluate the limit by substituting x equal minus 1 into the expression, you get 0 over 0. That is an indeterminate form. Now you certainly can work it the way we did in Chapter 1, but L'Hopital's rule now applies. So what we're going to do then is we're going to take the derivative of the numerator, and this is a good review for the final. This is going to be 2x minus 1. And the derivative of the denominator is just going to be 1. So now you see this is the same thing by L'Hopital's rule. If I were giving a lecture in class, I would put LHR under here to indicate that this equality is because of L'Hopital's rule. But now we can plug in minus 3 and get minus 7. So that's the answer using L'Hopital's rule. And from a graphical point of view, you see that this function is not defined for x equal minus 3, but whether I approach from the left or from the right, let's say I did that wrong, from the left or from the right, I get closer and closer to minus 7. So this is indeed the correct answer. Let's do another example. We're going to evaluate the limit as x tends to infinity, and that means that the a in L'Hopital's rule can be either plus or minus infinity as well. And here we have x squared over e to the 3x. Now this is a limit that we could not do previously, and you can't plug infinity in, because if you were to plug infinity in, you would get infinity over infinity. So you see this is and in fact that's what we do here. If we plug in this, we get infinity over infinity when we plug it in directly. So let me start at the beginning, I guess. So as x approaches infinity, this approaches infinity over infinity. That's not 1. It's because this is an indeterminate form. We don't know what infinity over infinity is. So to use L'Hopital's rule, we differentiate the numerator and the denominator and evaluate the limit. So here, the limit as x tends to infinity of this is equal to, by L'Hopital's rule, if I differentiate the numerator, I get 2x. If I differentiate the denominator, I get e to the 3x times 3. Now, when I take the limit as x tends to infinity, the numerator still goes to infinity, and the denominator still goes to infinity. So this is another indeterminate form. But since this satisfies the if part of L'Hopital's rule, we can apply it again. So we're doing L'Hopital's rule again. Now we get 2. The derivative of 2x is 2. The derivative of the denominator is the 3 just sits there, and the derivative of e to the 3x is 3 e to the 3x. So the net of all that is I get 9 e to the 3x. And now, as x tends to infinity, the top remains 2, but this gets infinitely large, which means that this is 0. Thus, as x approaches infinity, this expression approaches 0. And if you think about that, that means that exponential growth will trump quadratic growth every time. And if you think about this a little harder, exponential growth will trump any polynomial up here. So anyway, as x approaches infinity, this expression approaches 0. This indicates that the graph has a horizontal asymptote at y equals 0. As x gets larger and larger, this gets closer and closer to 0. Now, there are other indeterminate forms that we can also be clever and apply L'Hopital's rule to. And some of them, and this will work for all of these examples, if I get 0 raised to the 0 power, 1 raised to the infinity power, or infinity raised to the 0 power, they're also indeterminate forms. But we can use logarithms that we're using algebra, to rewrite the form as a ratio and then use L'Hopital's rule. An example is worth a lot of words, but what we end up doing is we end up taking natural logarithms and then we invert the logarithms. So here we go with this. We're going to evaluate the limit as h goes to 0 of 1 plus h to the 1 over h. Now if we're plugging this in, you see we would have 1 raised to the infinity. So this is of the form 1 to the infinity. Okay. As h approaches 0, the base 1 plus h approaches 1, and the exponent 1 over h approaches infinity. Thus we have the indeterminate form 1 to the infinity. So we're going to let y equal this expression. And then we're going to take the natural logarithms of each side. Now that has the effect of, as we talked about with logarithmic differentiation, that has the effect of knocking out the exponent, bringing it down in line. So when we take this is what we're letting y be. The natural logarithm of y is the natural logarithm of this. The exponent can come down in front using a property of logarithms. And so we have ln of y is ln of 1 plus h over h. Now as h approaches 0, we have the numerator. This, we can just plug it in. This approaches ln of 1 and we get 0. And for the denominator, as h goes to 0, we get h is equal to 0. Thus, this approaches an indeterminate form, 0 over 0. So we can use L'Hopital's rule. So the limit, as h goes to 0 of ln of y, is equal to the limit as h goes to 0 of this. But now we're going to use L'Hopital's rule. The derivative of the numerator is 1 over 1 plus h, because the derivative of the ln of u is 1 over u. And the derivative with respect to h of the denominator is just going to be 1, and so we get this. And so this is the limit as h goes to 0 of something over 1 is just the something, so we have this. And so the limit as h goes to 0 of this is equal to just 1. So we evaluate the limit. But this was the limit of the natural logarithm. So since the natural logarithm, the limit as h goes to 0 of the natural logarithm of y is equal to 1, we also know that the limit as h goes to 0 is equal to, and you see this is log base e, so this is going to be y instead of ln y. So you see if ln y is equal to 1, then y is equal to e, but this was the limit. So this is e to the 1. That's just the definition of natural logarithm, and that's equal to e. Therefore, this limit is equal to e. As a final example, we're going to look at the indeterminate form of infinity minus infinity. We can use L'Hopital's rule in cases where the limit is of the indeterminate form infinity minus infinity. The expression is first written as a ratio using algebra, and then, if possible, L'Hopital's rule is applied. So let's look at the example of the limit as x goes to infinity of the square root of x squared plus x minus x. As x tends to infinity, this expression, if we plug it in, we will get infinity and minus infinity, which is an indeterminate form. So before we can use L'Hopital's rule, we must rewrite this as a ratio. So first thing we do is, and this is some algebra, we will factor x squared out of in the radical. And notice that what this means is x squared times 1 is x squared, and x squared times 1 over x is x. So that factoring is good, and then this is minus x. So that was factoring. But now the square root of x squared is equal to x if x is bigger than 0, and since we're going to positive infinity, we can assume that. So this is x, and this is the square root of 1 plus 1 over x minus x. But now we can look at this a little bit more. You see, this is x times this square root minus x, so I can factor x out of both of them. So this is going to be x times the square root of 1 plus 1 over x. That was this term right here. And this is x times 1, so that is minus 1. Now you see, this is going to be the numerator, but now we're going to write x as 1 over x. We're writing x as 1 over x. Now we've turned the expression into a ratio, as we suggested we would do up here. Now note that as x approaches infinity, both the numerator and denominator approach 0. You see, whenever x goes to infinity, the 1 over x here, this gets close to the square root of 1. Square root of 1 is 1 minus 1. And whenever x goes to infinity, this is 0. So this is 1 minus 1 is 0. This also is 0. That means this is an indeterminate form, 0 over 0. And we can use L'Hopital's rule. So now we take the derivative of the denominator. Now it's a good review for the final. This is x to the minus 1. So the derivative of that is minus 1 over x squared. Now this is two terms. Now the derivative of this 1 here is going to be 0, but this is going to be 1 plus 1 over x whole to the 1/2. So there's the chain rule and the power rule. So the derivative of this one is going to be 1/2 the quantity 1 plus 1 over x whole to the minus 1/2 times the derivative of what's inside. Well, the derivative of 1 is going to be 0, and this is going to be x to the minus 1, which is minus 1 over x squared. So you see, I get this is 1/2, 1 plus 1 over x to the minus 1/2 times the derivative of what's inside the radical. That is minus 1 over x squared. So you see, this little equal sign here was because we used L'Hopital's rule, differentiating the numerator and the denominator. But now when you look at this, you can see that I have 1 over x squared here and 1 over x squared here, so those will cancel one with another. And so I just have the numerator left, and this is the limit as x goes to infinity of 1 over 2, the square root of 1 plus x squared. But now I can take the limit of this as x goes to infinity, and as x goes to infinity, 1 over x goes to 0. So this is going to be 1 over 2 times the square root of 1, or 1/2. So this limit is equal to 1/2. And this indicates that the graph of this function has a horizontal asymptote at y equal 1/2. And here's a picture of how that would play out. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. May God bless you all.